Alright, Prop 38 says triangles which are on equal bases and in the same parallels are equal to one another. So it's just fitting the same pattern of the last few propositions, where we kind of proved something similar to this with parallelograms. Prop 37 was starting to move into areas of triangles. Same thing here. When we talk about these two triangles being equal, we don't mean congruent. We mean that the areas are the same. Okay, so how do we prove this? Well, I guess on the one hand, the only difference here between 37 and 38 is that now the triangles are no longer, they don't have the exact same base, we just are saying the bases are equal. So I'll write that out because we're given that. So we'll assume that BC is equal to EF. We're given that. And then we want to just go through and prove that the two triangles ABC and DEF are equal and that they have the same area. All right. How do we do that? Well, kind of a similar tactic to what we did in 37. We're going to try to change this into a problem involving parallelograms and then work down from there. So the first thing that we're going to do is we will construct, let's see, what do we call it? BG. BG is going to be parallel to AC. Yeah. So construct BG parallel to AC, and we'll also construct FH parallel to DE. Is that right? Yep. And both of those are from Prop 31 that allows us to make parallel lines. So let's see here. Let's use my compass to mark off AC and then come over to B. Swing that thing up and see where it crosses the line. That's the point of intersection that we are looking for. Let's see, can I get it right? It's about maybe right there. I guess I could have done the same thing with BC. Maybe that would have given me an even more accurate parallel line. All right, so there's G. And right, same thing with DE. Yeah, maybe this time I will use EF, because we know that from one of the previous propositions that in the parallelogram, which is what we're trying to create, the opposite sides are equal length. So it really doesn't matter. It should come out to the same thing either way. But we'll do it two different ways. Keep things fresh. Alright, so there's H. Alright, so we've made our two parallelograms. Probably you can take it from here if you wanted to. Right, so yeah, we just formed GBCA and DEFH, which are both parallelograms. But notice, since, how should I say this? Since GBCA and DEFH have equal bases, and fall between the same parallels, what do we get? Well, we get that they're equal in area. GBCA equals DEFH. And that was, let's see, I need to cite that. That was from Prop 36. Yep. Okay. But notice that in both of these, we have the diagonal that bisects them. So maybe I'll say more, we have that triangle ABC is equal to triangle ABG. And maybe I'll just try to do this all in kind of one line. DEF, triangle DEF equals triangle DFH. And this is, at least for this first piece, because AB bisects GBCA and DF bisects DEFH. And that was prop 34 that says the diagonal bisects the parallelogram. Then maybe I'll say GBCA is equal to triangle ABC plus triangle ABG. But since ABC equals ABG, this is really the same as ABC plus ABC. And same idea with DEFH is equal to DEF plus DFH, but DEF and DFH are equal in area. So it's really DEF plus DEF. And then we've already stated that these two parallelograms are the same. GBCA is equal to DEFH. So ABC plus ABC equals DEF plus DEF. And I'll just kind of like put this as a note on the side. It's probably really obvious. This is the same as saying that 2 times ABC is equal to 2 times DEF. So the way that we kind of think about it is you can divide out the 2 to get that ABC equals triangle DEF. Right. Yeah, and this is another one of the situations where, so the way that Euclid kind of wrote it out is he pointed out that AB bisects GBCA, so ABC is half of GBCA, and for the same reason DEF is half of DEFH, and then he says, but the halves of equal things are equal to one another, and from that he concludes that ABC equals DEF. So he kind of, of course, the Greeks, they didn't really think about things in terms of this, like they sort of intuitively thought about it this way, but they maybe not symbolically wouldn't have thought about it this way, because when they were talking about areas, they didn't really think about areas as like a quantity. I mean, I guess in some respects they kind of did, but they didn't really, reduce an area and be like, oh, the area of ABC is 7.5. And so the area of DEF is also 7.5. So they didn't, this would be a little bit, this kind of notation maybe be a little bit foreign for them or a little bit unusual for them, but the intuition is the same, and the intuition is kind of what they relied on. So, right, there we have it. ABC equals DEF. QED, therefore, etc.